Today I'd like to go over a problem, and in so doing discuss the concepts of work, kinetic and potential energy, and how the network can result in a change in kinetic energy, or in some cases it can result in a negative change in potential energy. I also would like to go over what a conservative force is and what a non-conservative force is in this problem. Okay, so we're going to do a work energy problem, the skier going down the slope. Okay, so let me go ahead and draw that skier. Okay, so here we have the slope, and let's say that that is at a 30-degree incline. Here's the skier. Okay, so there's our skier going down the slope. The slope happens to be a total distance of 500 meters from the start to the finish. Alright? Good. Now, I'm going to put a constraint on here that we're not going to be able to use Newton's laws or Galileo's equations. So for this one, do not use Newton's laws, at least primarily don't use them, or Galileo's kinematics equations. So don't use them. We're just going to use the concepts of work and energy to do this. Alright. Well, the first thing I want to do, now that I said don't use Newton's laws, well, we're going to have to at least draw a force diagram. Okay, so we have the person's weight. Let's give the person a mass. Let's say the person's mass is 60 kilograms. Okay, let's say that there is some there's some friction between the bottom of the skis and the snow. So let's say that we have the coefficient of kinetic friction is equal to 0.1. And we know that the slope is 500 meters from start to finish. Okay, so let me lay out the person's weight here. The weight would be equal to mg, and so that would be 60 kilograms times 9.8, and so that gives us 588 newtons of weight. And we can split that person's weight up into a component perpendicular to the slope and a component parallel with the slope. So this angle is 30 degrees here. This downslope component would be 588 sine 30, which is half of 588 or 294 newtons. The component perpendicular to the slope would be 588 cosine 30, and that is equal to 509 newtons. The normal force would be the force of the slope pushing up on the person, and I'll just label that N, and that would be equal and opposite to this component right here. So N would also have a magnitude of 509 newtons, since that's the only force acting on the skier besides friction. Friction, of course, is opposing the skier's motion, so I can label that F, and friction, as we remember, is equal to the coefficient of kinetic friction times the normal force. Coefficient of kinetic friction is already stated as 0.1. So I'll put that there. Times the magnitude of the normal force, which is 509 newtons. And so that gives us 50.9 newtons of frictional force. So that's equal to 50.9 newtons. That's for the force of friction. Okay, now if we were to do it the way we just learned in the past unit, we would take F equals ma, solve for acceleration, find the velocity, and do all of that kind of stuff. Remember, this time I said let's not use it. We're going to just strictly use work and energy pretty much for the most part. Alright, so by that I mean we're going to need to use the idea of the law of conservation of energy and work. Okay, well, first of all, let's consider the amount of work done by these different items, these different forces, I should say. Let's consider the work done by gravity on the skier. Well, the component of gravity that is along the direction of the slope, that's 294 newtons. Remember, work is equal to force times distance, where the force is in the same direction as the displacement. So we could go ahead then and say that the force due to gravity is 294 downslope newtons, and then we'll multiply it by that distance of 500 meters, and we will get 294 times 500, and that gives us 147,000 Newton meters, or joules. 1 Newton meter is defined as 1 joule. Okay, so that's the work done by gravity on the skier. What about the work done by the normal force on the skier? Well, we'll use our dot product again, F dot distance, and remember, that's equal to the magnitude of the force times the distance traveled times the cosine of the angle between, right? But notice the normal force is at 90 degrees. So this is cosine of 90 degrees. Okay? And the cosine of 90 degrees is equal to 0. So that means the work done by the normal force is 0 joules. And that brings up a very good point. Anytime you have a force and it is perpendicular or 90 degrees to that of the direction of motion, the work done on that object is 0. How about the work done by friction? Well, the work done by friction, we can use a similar logic. Work is force dot distance. I should really be more careful with that. That'd be the frictional force this time, magnitude of that, times the distance traveled, times the cosine of the angle between. But notice friction is pointing the opposite direction compared to the direction of motion. friction is pointing upslope, the direction of motion is downslope, so that's a cosine of 180 degrees. And what's the cosine of 180? -1. So we're going to end up with a negative amount of work here. The frictional force we already found out was 50.9 newtons. The distance is 500 meters times a -1 because of the fact that friction is pointing the opposite direction of the motion. Friction is losing the battle, in other words. So if we take that, multiply them together, we get 50.9 times 500 times a -1. We get let me double check that again here. We get 25,450. Negative though. Negative 25,450 joules. Okay, so if we check our energy budget here, the amount of work done by the different items we have, the work done by gravity is a positive 147,000 joules. We have the work done by the normal force is 0 joules. We have the work done by friction, that's equal to a negative 25,450 joules. So what's the amount of net work done on the skier? Well, we can add those up, and that would give us how much? Well, let's see. So we'll take 140, so the net work would be equal to 147,000 joules minus, or in other words, plus a negative 25,450 joules and that gives us, let me just go ahead, 147, that gives us 121,550 joules. That's the net work done on the skier. All right. So this is taking it from looking at it from a work perspective. From the work perspective, we can see that gravitational force does work. The normal force does no work on the skier. And friction does work on the skier, but it's a negative amount of work done on the skier. Friction lost the battle. That downward component here of gravity won the battle, you might say. The net work done on the skier is 121,550 joules. Okay. Now it turns out that there are a couple different kinds of forces. One kind of force is known as a conservative force. A conservative force is one where the amount of work does not depend on the path taken. So, for example, if we think of gravitational force, gravitational force is a conservative force. So there's an example. Why? Because it doesn't matter which path you take, you still end up doing the same amount of work to oppose gravity. So let's say that here's the ground, and we're going to raise an object of a certain mass from point A to point B, and we're going to take this path to get to point B. The amount of work done to overcome gravity would be the same going from A to B that way as if we went like this from A to B, or like this from A to B. It doesn't matter. It does not depend on the path taken. When we get that mass to point B, that mass is going to have the same amount of potential energy in each case. And since we're only considering the gravitational force and not friction, it does not matter what path. It takes the same amount of work to overcome gravity there as here and as here. Same amount of work done to oppose gravity. Independent of path. So gravity then is a conservative force. On the other hand, a non-conservative force and I'm sure you can guess, is where the work depends on the path. So work does depend on the path taken. So a good example of that one would be the frictional force. Okay, so if we had to go from point A to point B and there was friction acting the whole way, you can see that there's a whole lot more friction because there's a longer path taken here than if we just go straight from A to B straight up. Look, this path is shorter, so there's less total frictional force here and more here. So friction is a non-conservative force. That means that we're going to have more work to overcome friction in this case, and less work to overcome friction in this case here, because there's less path length. So if the work does depend on the path taken, that means that force is a non-conservative force. Another example, so that's example number one, here's example two, would be the propeller force of an airplane in a plane. Okay, you can see the propeller would be doing more work if it had to do loops and so forth and fly a longer path than if it just took a shorter path. So there are two examples of non-conservative forces: friction force, propeller force. Main example of conservative force would be gravitational force. Another one would be, let's say, electrical force or magnetic force, something like that. Okay, now we can get back to our original problem. And let's deal with a couple questions. Let me get this down here so we can see it better. Okay, one would be, how much potential energy is at the top? So let's say find the potential energy at the top. Potential energy of the skier at the top. Another question might be, how much work is done by friction? We already got that part right. Another part might be something like, what's the kinetic energy of the skier at the bottom? And then maybe a fourth part of the question might be, what is the skier's velocity at the bottom of the hill? So those are some questions we could address. All right. Now we've already found the net work done by the skier by using the work perspective idea. We found the work done by gravity, we found the work done by the normal force, we found the work done by friction, we added them all up and we got the net work. We'll keep that in mind for later. Okay. For now though, let's look at the law of conservation of energy. Well, first of all, let's address question number 1. What's the potential energy? Well, potential energy, or capital U, gravitational-wise, is equal to mass times gravity times the height. So we need to find the height of the skier at the beginning. And so we need to maybe draw a distance triangle where this is 30 degrees, this is 500 meters here for the hypotenuse, and we need to find this height here. Okay, well that shouldn't be too much of a problem. H would be what? 500 times the sine of 30 degrees, half of 500, so that's 250 meters. So H is equal to 250 meters. We could go ahead then and plug that in. We have 60 kilogram mass of the skier, 9.8 for gravity, and the height is 250 meters. We end up with 147,000 joules. That number sounds awfully familiar. Let's look on the previous page and see what that... Oh my gosh, that was the work done by gravity on the skier. That's the same number. So the potential energy of the skier at the top of the hill, right here, is the same value as the work done by gravity on the skier and moving the skier from the top of the hill down to the bottom. That's not a coincidence, folks. Okay, so we've answered the first one. We found that the potential energy at the top was 147,000 joules. Okay, good. Now let's look at the second question. What was the work done by friction? Well, we found the force due to friction before. That was 50.9 newtons. That was just the coefficient of friction times the skier's times the normal force right here. Okay, mu times the normal force, that gives us 50.9 newtons. And then what did we do? We multiplied it by the distance moved, 500 meters, and then multiplied by a cosine of 180 because we saw that frictional force is pointing to the right, the displacement of 500 meters is pointing to the left, the angle between them is 180 degrees, cosine of 180 is -1. So we got negative 25,450 joules. Okay, now let's look at the kinetic energy at the bottom. How can we get that? Well, a couple ways. Okay, I'll just move over here a little bit. We can use what's called the law of conservation of energy. This is one way. Okay, and basically it goes something like this. We can take the, let's say this is position 1 up here, or position 1 up here, and this is position 2 down at the bottom. So we can express it like this. We have the potential energy, gravitational potential energy at position 1, plus the kinetic energy at position 1, plus the work done by friction, equals the potential energy down at the bottom, position 2, plus the kinetic energy down at the bottom, and that should work just fine. Now we have to add that work done by friction because there is a non-conservative force involved in this problem. And so if there wasn't friction, then it would just be U1 plus K1 equals U2 plus K2. But since there is friction, we have to add that term in on this left-hand side. Okay, we already found the potential energy at the top, so I'll plug that right in, 147,000 joules. The kinetic energy at the top, oh, I forgot to mention, the skier is starting at rest, so V1 is equal to 0. Remember, kinetic energy is 1/2 mv squared, so it's just 1/2 m times 0 squared, so that whole term just drops off. That's 0. The work done by friction, that's negative, isn't it, in this case? Okay, so that'd be a minus 25,450 joules. What's the potential energy at the bottom? Well, the bottom we can define as 0 height. So therefore, if it has 0 height and potential energy is m times g times h, that would be m times g times 0, or just 0. So that term drops off. And so we're left with kinetic energy 2, or the kinetic energy at the bottom. So that gives us 147,000 minus 25,450. And so that leaves us with 121,550. Well, that sounds very familiar again. That's joules. That's equal to the kinetic energy, in other words, the kinetic energy at the bottom. I seem to remember that number, and yes, sure it is. Here it is again. 121,550. That was the net work done on the skier. And we found here that that's the kinetic energy at the bottom. So, strange but true. That must mean that the change in kinetic energy from the skier going from the top of the slope down to the bottom, the change in kinetic energy of the skier is equal to the net work done on the skier. See, the same value. Kinetic energy at the bottom, the kinetic energy at the top was 0, so that'd just be this minus 0 is this. That gain in kinetic energy there is equivalent to the amount of net work done by gravity, by friction, and by the normal force. This is called the work energy theorem. And it's a very powerful relationship, one that is very useful. So I'm going to put a star next to that one. It turns out that there's also a relationship for potential energy, that the net work, excuse me again for this light, the net work can also be equated to potential energy. That's the negative of the change of potential energy. So it's just the opposite sign of that of the kinetic. So if there is a change in potential energy, it would be the negative change. Okay? So we found the kinetic energy. We also found that there's a very important relationship called the work-energy theorem, which says that the net work results in a change in kinetic energy, a positive change in the kinetic energy, or a negative change in the potential energy. Last thing, we want to find the skier's velocity at the bottom, where the skier started out, let's say, at 0 velocity at the top. Okay, well, if we know the kinetic energy at the bottom, we can certainly find the velocity, because remember, kinetic energy is equal to 1/2 mv squared. So we can just go ahead and substitute our values in. It's 1/2, and then 60 for the mass of the skier, and V2 is what we want to find. So if we go ahead and do the math, we get that V2, or the velocity at the bottom, in other words, is 63.6 approximately meters per second. We didn't have to use Galileo's equations of motion. The only part of Newton's laws we had to use was maybe like draw a force diagram. We used the fact that work and energy concepts are extremely helpful, where work is force dot distance, potential energy is m times g times h, kinetic energy is 1/2 mv squared, and the law of conservation of energy states that the potential energy plus the kinetic energy plus any non-conservative force is at one position is equal to the potential energy plus the kinetic energy at some other position along the slope. This right here is a non-conservative force. Friction is a non-conservative force, so this right here depends on the path length, whereas potential energy and kinetic energy by themselves are just they're dependent upon the gravitational force, which is a conservative force. Thanks a lot, guys.